A pleasant greetings to all. In this video, I am going to explain the transfer function of mechanical translational system. For explaining this, I am going to consider a problem. Write the differential equations governing the behavior of the mechanical system shown in figure. Also obtain the analogous electrical circuits based on a force current analogy and force voltage analogy. Also find the transfer function x1 of s by f of s. Consider this mechanical system. This mechanical translation system consists of two displacements x1, x2, two masses m1, m2, two springs k1, k2 and one frictional element v1. Here, the first one is draw the free body diagram. Here two displacement is corresponding to two equations. For x1 we are having one equation, x2 also we are having another one equation. So here this is the free body diagram. So to draw the free body diagram, we have to consider two masses. For the mass m1, external force acting on the mass m1 is F of t. What are the internal forces? K1, F1 due to mass m1 also. So due to mass m1, the internal forces m1 into d square x1 divided by dt square. Then first spring element K1 into x1. Second spring element is connected between two displacements x1 and x2. So how to write this? K2 into x1 minus x2. Next, consider the mass m2. Mass m2, there is no other external forces acting on it. All are internal forces. One is m2 into d square x by dt square. Another one is k2 into, with respect to x2 you have to write x2 minus x1. And next also the same free body diagram, here have to change the direction of this one. So now the direction is inward direction. If we change this direction as the inward direction, here the values also terminals also change. So how to write this? K2 in the x1 minus x2. This is the modified free body diagram. Next, I am going to write the equation. The first equation is due to mass m1, F of t, that is the external force. The internal forces are due to mass m1 into d square x1 by dt square. Then F1 into dx1 by dt due to frictional element and due to spring element k1 into x1 and another one spring element k2 into x1 minus x2. This is equation number 1. Equation number 2 is m2 into d square x2 by dt square plus k2 into x2 minus x1 equal to 0. And next draw the mechanical network. Here this is the mechanical system. So we have to draw the mechanical network. Considering the mass m1, the force acting on the mass m1 is F1. So first draw F of t. Then across the F of t, first draw m1. Then what are the elements that is connected to m1? That is k1 and f1. Next you have to write the element that is connected between two displacements x1 and x2. So in between you have to draw k2. And k2 is connected with m2 also. So this is the mechanical network. And from the mechanical network, I am going to draw the electrical network using force current analogy. For the force current analogy, force is equivalent to current. Then C is equal to M, L is equal to 1 by K1, then R is equal to 1 by F. In this way, directly have to put the values in the mechanical translational network. Here, for the force current analogy, we have to use the series circuit, the same circuit, there is no change. Here instead of f of t, I am using I of t. Instead of C1, M1, I am using C1. Instead of K1, I am using 1 by L1. So here write L1 is 1 by K1. Then instead of F, I am going to write R1. Here L2 is 1 by K2. And here C2 is M2. This is the force current analogy. Next, I am going to explain the force voltage analogy. For the force voltage analogy, we have to apply in a series circuit. Force is equivalent to voltage and L is equal to M, C is equal to 1 by K, then R is equal to F. That's all. Now I am going to apply. Here series elements are converted into parallel and parallel connections are converted into series. F of t, I am going to put E of t first, and this is the voltage. And next L1 equal to M1, and next connected in series with K1, C1, again series with F1, that is equal to R1. Next K2 and M2 are connected in series, both should be in parallel. So C2 is 1 by K2 and L2 is M2. So this is the force voltage analogy.